Right now, there are over 5,000 confirmed exoplanets orbiting distant stars, worlds of unimaginable diversity, planets where it rains molten glass sideways, where years last only hours, where two suns paint the sky in colors we've never seen. Yet here's the crushing truth that space agencies don't advertise: we will never set foot on any of them. Not because we lack ambition or technology, but because the universe itself has built insurmountable barriers between the stars. The distances are so vast, the energy requirements so impossible, and the human body so fragile that interstellar travel might forever remain a beautiful dream. Today, I'm going to show you why the stars will always be out of reach, and why that reality is both heartbreaking and profoundly meaningful. If you're fascinated by the harsh realities and mind-bending mysteries of our universe, make sure to subscribe to this channel and give a thumbs up. Now let's begin this journey. Let's start with the most fundamental barrier: the sheer, incomprehensible distances between stars. The nearest star system to Earth is Proxima Centauri, a red dwarf star 4.24 light-years away. That number sounds deceptively small until you translate it into human terms. Light, the fastest thing in the universe, takes over 4 years to make that journey. In kilometers, that's about 40 trillion, a number so large our brains simply can't process it meaningfully. To put this in perspective, Voyager 1, launched in 1977 and currently humanity's most distant spacecraft, is traveling at about 17 kilometers per second. At this speed, it would take Voyager 73,000 years to reach Proxima Centauri if it were headed in that direction, which it isn't. 73,000 years ago, our ancestors were just beginning to develop language. The entire history of human civilization, from the first cities to smartphones, spans only about 10,000 years. But Proxima Centauri is practically next door in cosmic terms. The exoplanets that capture our imagination, Kepler-4, 52b, the Earth's cousin that might harbor life, or HD 189733b, where a year lasts only 2.2 days, these worlds are hundreds or thousands of light-years away. Kepler-4, 52b, often called Earth 2.0, sits 1,400 light-years from us. Even traveling at the speed of light, which physics forbids for anything with mass, the journey would span 14 centuries. The energy requirements for interstellar travel are equally crushing. According to Einstein's special relativity, as you accelerate an object, its mass effectively increases, requiring ever more energy to continue accelerating. To accelerate a single kilogram to just 10% of light speed would require energy equivalent to the entire annual energy consumption of Switzerland. For a realistic spacecraft weighing thousands of tons, we're talking about energy requirements that dwarf humanity's entire energy production throughout history. The Parker Solar Probe, humanity's fastest spacecraft, reaches speeds of about 200 kilometers per second when swooping close to the Sun. This incredible velocity, which would get you from New York to Los Angeles in 20 seconds, represents only 0.067% of light speed. Even at this record-breaking pace, a journey to Proxima Centauri would take over 6,000 years, and the Parker Solar Probe achieves these speeds only by falling toward the Sun. It couldn't maintain them for interstellar travel. But speed isn't just about engines and fuel. As spacecraft accelerate to significant fractions of light speed, they encounter a deadly phenomenon: interstellar medium bombardment. Space isn't empty, it contains about 1 hydrogen atom per cubic centimeter on average. At low speeds, these atoms are harmless, but at 10% light speed, each hydrogen atom hits with the energy of a rifle bullet. At 50% light speed, the radiation from these collisions would kill any human crew within minutes, regardless of shielding. The human body itself becomes a prison at these scales. We evolved for Earth's specific conditions, its gravity, its magnetic field protection, its day-night cycle. In the zero gravity of space, our bones lose density at about 1% per month. Muscles atrophy. Fluids redistribute, causing vision problems and potentially permanent damage. The psychological toll of confinement, isolation, and the knowledge that Earth is impossibly far away could break even the strongest minds. Consider the generation ship concept, a massive vessel where multiple generations would live and die during the journey. For a trip to Kepler-4, 52b at 1% light speed, we're talking about 140,000 years of travel. That's about 5,600 generations of humans. The original mission would be ancient mythology to the arrivals. Languages would evolve beyond recognition. The colonists arriving would share almost nothing culturally or perhaps even biologically with those who departed. The radiation exposure during interstellar travel presents another insurmountable challenge. Beyond Earth's protective magnetosphere, cosmic rays, high-energy particles from distant supernovae and other cosmic events bombard everything. On a journey lasting decades or centuries, crew members would accumulate radiation doses that guarantee cancer, genetic damage, and cognitive decline. The shielding required to protect against this radiation would add so much mass to the spacecraft that acceleration to useful speeds becomes even more impossible. Speaking of seemingly impossible destinations, if you think reaching other star systems is challenging, you might be surprised by the difficulties of reaching even our neighboring planet. Check out my video, "This is Why We Will Never Reach Mars," where I explore the shocking barriers to colonizing the red planet. The link is in the description below and pinned on the comments. Now let's continue our journey through the cosmic obstacles that keep us earthbound. The Breakthrough Starshot project, announced in 2016 by Stephen Hawking and Yuri Milner, represents our most ambitious attempt to reach another star. The plan involves using powerful lasers to accelerate tiny spacecraft, each weighing just grams, to 20% light speed. Even this dramatically scaled-down approach faces staggering challenges. The lasers would need to generate 100 gigawatts of power focused perfectly on a sail just meters across as it races away at incredible speeds. Any slight imperfection in the sail or misalignment of the lasers would send the probe spinning off course. But here's the real kicker: even if Breakthrough Starshot succeeds, these nanoprobes can't slow down. They'll zip through the Proxima Centauri system in hours, snapping a few photos before disappearing forever into the void. After 20 years of travel, we'd get a few hours of data, and these are just tiny sensors, not vehicles that could carry humans or even meaningful scientific equipment. The time dilation effects of high-speed travel, often portrayed as a benefit in science fiction, actually create profound problems. Yes, at 99% light speed, time passes about 7 times slower for the travelers. A journey to a star 100 light-years away might feel like only 14 years to the crew. But here's what nobody talks about. Everyone they knew on Earth would be dead. Their entire civilization might have collapsed or evolved beyond recognition. They wouldn't be explorers returning with tales of distant worlds. They'd be refugees from the past, forever exiled from everything they knew. Let's examine the most optimistic propulsion concepts and why they still fall short. Nuclear pulse propulsion, studied in the 1960s under Project Orion, involved detonating nuclear bombs behind a spacecraft to push it forward. In theory, this could achieve 3 to 5% light speed, but you'd need millions of nuclear explosions, each precisely timed and positioned. The radioactive contamination, the mechanical stress on the ship, and the sheer insanity of riding nuclear explosions through space make this a non-starter. Fusion rockets, still theoretical despite decades of research, might achieve 10% light speed under ideal conditions, but ideal means perfect efficiency unlimited fuel, and engineering solutions we haven't invented. The ITER fusion reactor, under construction in France, will weigh 23,000 tons and require a building the size of a sports stadium just to produce power. Now imagine miniaturizing that, making it work reliably for centuries and accelerating it to relativistic speeds. Antimatter propulsion offers the best theoretical performance. Matter and antimatter annihilation converts 100% of mass into energy. But humanity has produced only nanograms of antimatter in all of history, at a cost of trillions of dollars per gram. Storing antimatter requires perfect magnetic containment. One power failure and your fuel annihilates your ship. Even if we could produce and store antimatter efficiently, the gamma rays from annihilation would cook the crew regardless of shielding. The Fermi paradox takes on new meaning when you understand these barriers. We don't see evidence of alien civilizations not because life is rare, but because the universe has trapped every civilization in their home world. The great filter might simply be the speed of light and the vast emptiness between stars. Every intelligent species in the universe might reach the same conclusion we're reaching: the stars are forever out of reach. Solar sails offer elegance but not solutions. Yes, they require no fuel, using radiation pressure from stars to accelerate. But the acceleration is glacial, millimeters per second squared. To reach useful interstellar speeds would take centuries of acceleration, and as you move away from the Sun, the pressure drops with the inverse square of distance. By the time you reach Jupiter's orbit, the push is 25 times weaker than at Earth. In interstellar space, it's essentially zero. The psychological barriers might be even more insurmountable than the physical ones. Humans evolved in small tribes, exploring territories they could walk across. Our minds aren't equipped for journeys where departure and arrival are separated by millennia. The crew of a generation ship would need to maintain complex technology, social cohesion, and mission purpose across thousands of generations. Every generation ship study has concluded that social breakdown, mutiny, war, or simple loss of purpose is virtually inevitable over such timescales. The economic reality delivers another crushing blow to interstellar dreams. The Apollo program, which put 12 humans on the moon for a few days total, cost about $300 billion in today's money. A realistic interstellar mission would cost thousands of times more, likely exceeding the entire global GDP for multiple years. No nation or coalition of nations could justify such expenditure when we have pressing problems on Earth. The opportunity cost is staggering. Every dollar spent on interstellar travel is a dollar not spent on climate change, poverty, disease, or education. Even communication with interstellar missions faces impossible barriers. Radio signals weaken with distance according to the inverse square law. A signal from Proxima Centauri would be 10 billion times weaker than the same signal from Mars. The Deep Space Network, humanity's most sensitive radio receivers, would need dishes kilometers wide to detect transmissions from even the nearest stars. And with a 4-year delay each way, troubleshooting any problems becomes impossible. The mission would be truly alone. The materials science challenges are equally daunting. Any interstellar spacecraft would need to function perfectly for centuries or millennia, but every material degrades over time. Cosmic rays cause metal fatigue, micrometeorite impacts accumulate, seals degrade. Electronics fail. The Voyager spacecraft, built with 1970s technology, are already showing their age after less than 50 years. Most of their instruments have failed or been shut down to conserve power. How could we build something to last 1,000 times longer? Let's consider the biological barriers more deeply. The human genome accumulates mutations over time, especially under radiation exposure. Over thousands of generations on a generation ship, genetic drift could lead to serious health problems or even speciation. the crew arriving at their destination might no longer be genetically compatible with Earth humans. They would have evolved into something new, shaped by the unique selective pressures of their artificial world. The discovery of exoplanets, rather than bringing other worlds closer, has emphasized how unreachable they are. The Kepler Space Telescope and its successor, TESS, have shown us that planets are common. Nearly every star has them, but they've also revealed how alien these worlds are. Hot Jupiters orbiting their stars in days, super-Earths with crushing gravity, tidally locked planets with one side in eternal day, the other in eternal night. Even Earth-like planets orbit stars very different from our Sun, bathed in radiation that would sterilize any Earth life. The James Webb Space Telescope can analyze the atmospheres of exoplanets, detecting potential biosignatures from dozens or hundreds of light-years away. This is both exciting and heartbreaking. We might detect signs of life on distant worlds, oxygen atmospheres, organic molecules, even industrial pollutants from alien civilizations. But we'll never be able to visit them. We'll be like prisoners watching videos of places we can never go. Time itself conspires against interstellar travel. The universe is 13.8 billion years old, but complex life on Earth has existed for only about 600 million years. Humans have had technology for a few thousand years, spaceflight for less than 70. On cosmic timescales, technological civilizations might be fleeting, candles that flare briefly before extinguishing. By the time a generation ship reaches its destination, the civilization that sent it might be extinct, and any civilization at the destination might have risen and fallen multiple times. The expansion of the universe adds another temporal barrier. Due to dark energy, the universe's expansion is accelerating. Galaxies are moving away from each other faster and faster. In about 100 billion years, all galaxies outside our local group will have receded beyond the cosmic horizon, invisible and unreachable even at light speed. We're living in a brief window of cosmic history when other galaxies are even visible. Future civilizations will see a much lonelier universe. Even if we solved every technical problem, the ethical questions are staggering. What right do we have to condemn thousands of generations to live and die in a metal can, pursuing a mission they didn't choose? Generation ships would need strict population control, assigned roles, and limited freedom, essentially totalitarian societies. The colonists arriving at a distant world would have no connection to Earth, no loyalty to the civilization that sent them. They might choose not to colonize at all, having adapted to life in space. The discovery of extremophiles on Earth, organisms thriving in conditions once thought impossible for life, offers a cruel irony. Life is incredibly adaptable and resilient, able to survive in boiling water, inside rocks, in radioactive environments. But this same adaptability is precisely what we lack for interstellar travel. Humans are specialists, exquisitely adapted to a narrow range of conditions found only on Earth's surface. We're too complex, too fragile, too dependent on Earth's specific environment to survive the journey between stars. The rocket equation, first derived by Konstantin Tsiolkovsky in 1903, reveals the mathematical tyranny of space travel. To achieve high speeds, you need fuel. But fuel has mass, so you need more fuel to accelerate that fuel. This creates an exponential relationship where reaching even modest interstellar velocities requires fuel masses millions of times greater than your payload. For chemical rockets to reach just 1% of light speed, you'd need a fuel tank larger than the observable universe. The math doesn't just make it difficult, it makes it impossible. Consider what we've learned from the International Space Station about long-term space habitation. Despite being only 400 kilometers above Earth, resupplied regularly, and with crews rotating every 6 months, the ISS faces constant challenges. Water recycling systems break down, air leaks develop, psychological tensions arise even among carefully selected, highly trained astronauts. The station requires constant maintenance and occasional emergency repairs. Now imagine these problems compounded over centuries with no possibility of resupply or rescue. The biosphere. Two experiments in the 1990s attempted to create a closed ecological system in Arizona. Despite being on Earth with access to repairs and modifications, it failed spectacularly. Oxygen levels dropped dangerously, carbon dioxide scrubbers couldn't keep up, insect populations exploded while pollinators died off. The 8 crew members lost significant weight and suffered from chronic hunger. If we can't maintain a closed ecosystem on Earth for 2 years, how could we maintain one in space for millennia? Recent discoveries about the interstellar medium make the journey even more daunting. The space between stars isn't an empty vacuum, but contains dust, gas, and cosmic rays. The Voyager probes have revealed that the heliosphere, our Sun's protective bubble, shields us from much of this. Once you leave this bubble, radiation levels increase dramatically. The interstellar medium also contains denser regions that could damage or destroy spacecraft. We'd be sailing through an ocean we barely understand. The navigation challenges alone are staggering. Stars move relative to each other at tens of kilometers per second. Over a journey of centuries, your target star system will have moved significantly from where it was when you departed. You need to aim not where the star is, but where it will be, accounting for gravitational influences from every nearby star. A tiny error in calculation, compounded over light years, means missing your target entirely and drifting forever in the void. Let's examine the most habitable exoplanets we've discovered and why they're still impossibly hostile. Proxima Centauri b, the nearest potentially habitable exoplanet, orbits a red dwarf star that regularly erupts with stellar flares thousands of times more powerful than our Sun's. These flares would sterilize the planet's surface and strip away any atmosphere. TRAPPIST-1, with 7 terrestrial planets, subjects them to such intense radiation that complex life as we know it couldn't survive on any of them. The concept of terraforming other planets, often proposed as making them worth the journey, faces its own impossibilities. Mars, right next door, would require importing or generating an atmosphere, creating a magnetic field, and warming the planet, projects that would take tens of thousands of years with technology we can't imagine. Terraforming an exoplanet would be orders of magnitude harder, requiring equipment and resources that would need to survive the interstellar journey first. Even our robotic probes face severe limitations. Electronics degrade under cosmic ray bombardment. RTGs, radioisotope thermoelectric generators, that power deep space missions have half-lives measured in decades. Solar panels degrade and become useless far from any star. By the time a probe reached another star system, most of its instruments would likely have failed. We'd be sending dead metal on a one-way journey to nowhere. The light speed barrier isn't just a speed limit, it's a fundamental feature of causality in our universe. Information cannot travel faster than light without breaking cause and effect. Wormholes, if they exist, would likely collapse instantly or require exotic matter with negative energy density to stabilize. Alcubierre drives would need energy equivalent to the mass of Jupiter. Every proposed faster-than-light travel method requires physics that probably doesn't exist, or engineering that certainly doesn't. The cultural and linguistic barriers over generational timescales present another impossibility. Languages evolve rapidly. Old English from 1,000 years ago is incomprehensible to modern speakers. Over the timescales of interstellar travel, the crew's language would diverge so far from Earth's that communication would become impossible. Cultural drift would be even more extreme. The colonists arriving at their destination would share nothing culturally with the civilization that sent them. The gravitational challenges of interstellar travel compound every other problem. To reach high speeds, you need to accelerate gradually over long periods, but gravity from nearby stars will constantly perturb your trajectory. The gravitational influence of the Milky Way's spiral arms, giant molecular clouds, and the supermassive black hole at the galactic center all tug at a spacecraft over such vast distances. Maintaining the course would require constant corrections, consuming precious fuel and complicating navigation beyond current capabilities. Recent discoveries about space debris make the danger even clearer. The European Space Agency's Gaia spacecraft has mapped over 1 billion stars in unprecedented detail, revealing that space is far more crowded than we thought. Fast-moving stars, rogue planets ejected from their systems, brown dwarfs too dim to see, all pose collision threats. At relativistic speeds, hitting even a pebble-sized object would release the energy of a nuclear bomb. The odds of surviving such a journey approach zero. The medical impossibilities extend beyond radiation and bone loss. Human reproduction in space remains largely untested. Mammalian embryos have shown developmental abnormalities in microgravity experiments. We don't know if human pregnancy is even possible in zero gravity, or if children born in space would develop normally. A generation ship would need multiple generations of successful births in conditions that might make reproduction impossible or produce severe disabilities. Let's talk about what happens to the human mind over such timescales. Prisoners in solitary confinement develop severe psychological problems within months. Astronauts on the ISS, despite regular communication with Earth and beautiful views of our planet, report feelings of isolation and disconnection. Multiply these effects by thousands of years of confinement with no possible relief, no new environments, and no hope of return. The psychological breakdown wouldn't be a question of if, but when. The financial impossibility bears repeating with a different perspective. The world's combined GDP is about $100 trillion per year. A realistic interstellar mission would cost at least $1,000 trillion, 10 years of humanity's entire economic output spent on a mission that wouldn't return data for centuries and might never return at all. No rational civilization would make such an investment. The resources required would inevitably be allocated to more pressing needs. Water, that most fundamental requirement, illustrates the closed-loop challenges. The ISS recycles about 93% of water, with 7% lost to inefficiency. Over decades, this loss accumulates catastrophically. Starting with 1,000 tons of water and losing 7% annually, you'd have almost nothing left after 50 years. Yet, a generation ship would need to function for millennia. Perfect recycling doesn't exist in thermodynamics. Every process has inefficiency. The crew would slowly but inevitably run out of water. The social structure of a generation ship would require unprecedented social engineering. Someone must clean the waste recyclers, maintain the life support systems, repair failing equipment, jobs nobody wants, but everyone depends on. Over generations, class systems would emerge. Conflict would be inevitable. Human history shows that isolated societies tend toward authoritarianism, resource hoarding, and eventual collapse. There's no reason to think a generation ship would be different. Consider the information problem. A generation ship would need to store all of human knowledge, medical procedures, engineering specifications, cultural heritage. But data storage degrades over time. Cosmic rays flip bits in computer memory. No digital storage medium lasts forever. Physical books deteriorate. Even if you brought redundant copies, maintaining and updating this knowledge base over millennia would require resources the ship simply wouldn't have. The discovery that space is expanding faster than we thought makes some destinations forever unreachable, even in principle. Galaxies beyond a certain distance are receding faster than the speed of light due to cosmic expansion. Even if we could travel at light speed, which we can't, we could never reach these galaxies. They're fundamentally disconnected from us, separated by expanding space itself. Parts of the universe are literally impossible to reach now and forever. Even within our galaxy, stellar evolution works against us. Sun-like stars live about 10 billion years. More massive stars burn out in millions of years. By the time a generation ship reached its target, the star system might have changed dramatically. The star could have expanded into a red giant, engulfing its planets. It could have gone supernova. The habitable planet that motivated the mission might no longer exist. The concept of hibernation or suspended animation, popular in science fiction, faces biological realities that might be insurmountable. Freezing human bodies causes ice crystals that destroy cells. Chemical preservation requires solutions that are themselves toxic. The few animal species that truly hibernate do so for months, not centuries, and with specialized biology we don't possess. Every attempt to extend this to humans and longer timescales has failed. The energy density problem reveals another physical limit. The most energy-dense chemical fuel we know, hydrogen-oxygen, releases about 15 megajoules per kilogram. Nuclear fusion, if we could harness it perfectly, releases about 640 million megajoules per kilogram. This sounds impressive until you calculate what's needed for interstellar travel. To accelerate just 1,000 kilograms to 10% light speed requires about 4.5 times 10 to the 18th joules, equivalent to detonating 100 million tons of TNT. You'd need either impossible amounts of fuel or impossible fuel efficiency. The Voyager golden records, those beautiful messages to potential alien civilizations, illustrate our cosmic isolation perfectly. Voyager 1, our farthest probe, is currently 24 billion kilometers from Earth. It would take 17,000 years to travel just 1 light year at its current speed. The golden records were a message in a bottle thrown into an ocean so vast that the bottle will likely never be found. Even if aliens exist around Proxima Centauri, Voyager will take 70,000 years to travel that far, if it were headed that direction. Magnetic fields in space pose yet another unconsidered danger. The Milky Way has a complex magnetic field that pervades interstellar space. Charged particles from cosmic rays spiral along these field lines. A spacecraft would need to be carefully designed to avoid induced electrical currents that could damage electronics or create dangerous static buildup. The Parker Solar Probe, studying our Sun's magnetic field, has revealed complexities we're only beginning to understand. The interstellar magnetic field is even less understood. Let's examine what we've learned from Mars and why it's a preview of greater impossibilities. Mars is 180 times closer than the nearest star. The journey takes only 6 to 9 months compared to millennia. Yet despite decades of planning and billions in funding, we haven't sent humans there. The technical challenges, landing heavy payloads, protecting against radiation, producing oxygen and water, growing food, remain unsolved. If we can't conquer Mars, how could we possibly reach exoplanets? The temperature challenges are often overlooked. In deep space, far from any star, temperatures approach absolute zero, minus 270 degrees Celsius. All mechanical systems become brittle, fluids freeze, but near a star, temperatures soar. The spacecraft must somehow manage both extremes, maintaining livable conditions inside while protecting against wild temperature swings outside. Over centuries, thermal stress would fatigue even the best materials. Genetic diversity becomes a deadly problem for generation ships. Population geneticists estimate you'd need at least 10,000 people to maintain genetic diversity over many generations. Some studies suggest 50,000 is safer. This makes the spacecraft enormous, requiring even more impossible energy for acceleration. Smaller crews would inevitably face genetic bottlenecks, leading to increased birth defects, decreased resistance to disease, and eventual extinction. The discovery of rogue planets, worlds ejected from their star systems wandering alone through interstellar space, adds another hazard layer. Estimates suggest there might be billions of these dark wanderers in our galaxy, invisible until you're almost upon them. At relativistic speeds, you'd have no time to detect and avoid them. Hitting a rogue planet would obviously destroy any spacecraft instantly. The interstellar medium is far more dangerous than the empty void we once imagined. Consider the spare parts problem. Any complex machine requires maintenance and replacement parts. The ISS has regular resupply missions bringing spare equipment. A generation ship would need to manufacture everything from computer chips to medical equipment to clothing, all from raw materials that would also need to last millennia. The industrial base required would make the ship impossibly massive and complex. The political impossibility deserves examination. No government lasts long enough to complete an interstellar mission. The United States is less than 250 years old. The Roman Empire lasted about 1,000 years. China, with the longest continuous civilization, has seen countless dynasties rise and fall. Who would maintain funding and support for a mission spanning thousands of years? Political systems rise, fall, and transform on timescales far shorter than interstellar journeys. Entropy itself works against us. The second law of thermodynamics states that disorder always increases in a closed system. A generation ship is effectively a closed system. Over time, everything degrades, breaks down, becomes disordered. You can slow entropy with energy and effort, but you can't stop it. Eventually, inevitably, the ship's systems would fail. The crew would face cascading breakdowns with no possibility of rescue. The recent findings from the Event Horizon Telescope, which imaged black holes, remind us that the universe operates on scales that dwarf human concerns. These black holes are millions or billions of times the Sun's mass, warping space-time in their vicinity. Their existence reminds us how small and fragile we are. We're trying to cross distances measured in light years when we can barely sustain ourselves in low Earth orbit. The cosmic ray flux in interstellar space is far more intense than we initially understood. The Voyager spacecraft, after crossing into interstellar space, detected radiation levels 3 to 4 times higher than in the heliosphere. These aren't just dangerous, they're lethal over time. Cosmic rays include iron nuclei traveling at 99% light speed. When these particles hit spacecraft walls or human tissue, they create cascading showers of secondary particles. Shielding that could stop them would need to be meters thick, adding thousands of tons to the spacecraft mass. The failure of closed ecological systems on Earth should make us skeptical about space habitats. Beyond biosphere, 2. Consider the challenges of maintaining aquariums, terrariums, or even greenhouse ecosystems. They require constant adjustment, fresh inputs, and expert intervention. Ecosystems are chaotic systems with feedback loops we don't fully understand. Small changes cascade unpredictably. A generation ship's life support would be far more complex than any ecosystem we've attempted, operating for far longer, with zero margin for error. Light pollution from the home star creates an unexpected problem. As you accelerate away from our Sun, its light diminishes but remains the brightest object in your sky for years. This creates psychological issues, the crew watching their home star shrink, knowing they can never return. But it also creates technical issues. Solar panels become useless, temperature regulation shifts. The transition from stellar-lit space to the darkness between stars would stress every system designed with sunlight assumptions. The discovery of phosphine in Venus's atmosphere and methane variations on Mars show us that detecting life is possible. But this makes the isolation more poignant. We might detect biochemical signatures on exoplanets, oxygen, methane, industrial pollutants, proving life exists elsewhere. We might even detect technosignatures, evidence of alien civilizations. But we'll never meet them, never exchange knowledge, never join a galactic community. We'll be cosmic pen pals who can never meet in person. Asteroid mining, often proposed as a stepping stone to interstellar travel, faces its own impossibilities. The valuable asteroids, those rich in platinum, gold, and rare earths, are scattered throughout the solar system. Even within our solar system, traveling between asteroids requires months or years and enormous fuel expenditure. The infrastructure needed for asteroid mining would be staggeringly expensive and wouldn't bring us any closer to reaching other stars. It would just make us better at exploiting our local neighborhood. Consider what happens to knowledge over generational timescales. Information degrades through transmission errors like a photocopy of a photocopy. Over thousands of generations, scientific knowledge could devolve into cargo cult science, rituals performed without understanding why. The crew might maintain systems they no longer comprehend, following procedures that have become religious doctrine rather than engineering specifications. When systems failed in unexpected ways, they wouldn't have the knowledge base to innovate solutions. The microgravity problem has no solution compatible with current physics. Humans need gravity for health, but creating artificial gravity requires rotation. A rotating spacecraft experiences the Coriolis effect. Moving objects curve in flight, creating nausea and disorientation. The larger the spacecraft's radius, the less pronounced these effects, but this makes the ship enormous and harder to accelerate. There's no sweet spot where the ship is both large enough for comfortable artificial gravity and small enough for realistic propulsion. Recent studies of Mars analog habitats like HICs in Hawaii show that even carefully selected crews in simulated Mars habitats experience significant psychological stress during missions lasting just 8 months. Tensions arise, productivity drops, and conflicts emerge. These are volunteers who knew the mission would end, who could see Earth's sky, who had emergency evacuation options. A real generation ship crew would have none of these safety valves. The psychological pressure would be orders of magnitude greater. The speed of light creates a prison not just in space but in time. At 10% light speed, optimistically fast, a journey to a star 100 light-years away takes 1,000 years. During that millennium, technology on Earth would advance beyond recognition. The mission that left would be hopelessly obsolete by arrival. Worse, a faster ship launched 500 years later might overtake you, arriving first with superior technology. You'd arrive at your destination to find it already colonized by people who left long after you did. Dark matter, making up 85% of the universe's matter, presents hazards we can't even predict. We don't know what dark matter is, WIMPs, axions, or something else entirely. We don't know how it's distributed in interstellar space. We can't detect it except through gravitational effects. A spacecraft might be passing through dark matter clouds without knowing it, potentially experiencing effects we haven't imagined. We're sailing through an ocean we can't see, using maps that ignore most of what exists. The protein folding problem in biology reveals why we can't just send DNA and rebuild humans at the destination. Even if we sent genetic information, and artificial wombs growing humans requires the precise conditions found only on Earth. Proteins must fold into specific three-dimensional shapes to function, and this process depends on gravity, temperature, radiation levels, and countless environmental factors. We can't just print humans on arrival. Biology isn't software you can upload to new hardware. Stellar evolution timescales work against any long-term planning. Our Sun is about 4.6 billion years old, halfway through its stable life. In about 5 billion years, it will expand into a red giant, making Earth uninhabitable. This sounds like plenty of time, but consider that complex life took 3.5 billion years to evolve. On cosmic timescales, civilizations might be brief candles. Any target star system might go through similar changes during the journey, rendering the mission pointless by arrival. The quantum mechanics of interstellar travel reveals paradoxes we barely understand. At relativistic speeds, quantum effects become significant. The uncertainty principle means you can't know both position and momentum with perfect accuracy. For a spacecraft traveling at significant fractions of light speed, this uncertainty becomes macroscopic. Navigation requires precision we might not be able to achieve given fundamental quantum limits. The discovery of exoplanet atmospheres through spectroscopy is bittersweet. The James Webb Space Telescope can detect water vapor, carbon dioxide, even potential biosignatures in atmospheres light years away. We're developing the technology to study these worlds in detail to potentially confirm life exists elsewhere. But every detail we learn emphasizes how alien and unreachable these worlds are. We're becoming cosmic voyeurs, able to watch but never touch. Consider the governance problem on a generation ship. Who makes decisions affecting thousands of unborn generations? What political system could remain stable for millennia? Democracy requires informed citizens, but over generations, the original mission parameters would become ancient history. Authoritarianism might maintain mission discipline, but at what human cost? The ship might arrive with a population that has no interest in colonization, having adapted perfectly to life in their artificial world. The materials problem extends to basic wear and tear. Friction exists even in space, from what little atmosphere exists from thermal expansion and contraction from vibration. Moving parts wear down, seals degrade, metal fatigues. We design spacecraft for mission durations of years or perhaps decades. Scaling to millennia isn't just harder, it might be impossible. There are no 1,000-year-old machines anywhere on Earth because nothing can last that long with moving parts. Recent simulations of galaxy formation remind us that the universe is violent and dynamic. Supernovae explode, gamma-ray bursts sterilize regions of space, stars collapse into black holes. The Milky Way is relatively quiet now, but that's temporary on cosmic timescales. A generation ship might spend centuries traveling toward a target, only to have it destroyed by a nearby supernova before arrival. Space isn't a static backdrop, it's an active, dangerous environment. The energy storage problem is fundamental. Batteries discharge over time, even when not in use. Fuel tanks leak, imperceptibly perhaps, but over centuries, those tiny leaks become catastrophic. Nuclear fuel decays, chemical fuels degrade. You can't store energy for 1,000-year journeys using any known technology. The ship would need to generate power continuously, but power generation systems themselves require maintenance and have finite lifetimes. The psychological concept of future selves reveals why multi-generational missions are ethically dubious. Studies show that people treat their future selves almost like strangers. They'll make decisions that benefit them now at the cost of their future selves. Multiply this across generations. The people launching the mission sacrifice nothing. They die safely on Earth. The middle generations live and die in a tube for a mission they didn't choose. For arrivals, they'll never be. It's cosmic-scale exploitation of the powerless by the powerful. The expansion of human knowledge makes long-term predictions impossible. 1,000 years ago, we didn't know about electricity, evolution, quantum mechanics, or relativity. Our entire scientific worldview has been revolutionized multiple times in just a few centuries. Trying to plan a multi-thousand-year mission is like medieval scholars planning for our modern world. The assumptions underlying the mission would certainly be proven wrong, but the ship would be committed to a course based on obsolete science. The insurance and liability questions reveal practical impossibilities rarely discussed. Who is liable when a 1,000-year mission fails? Who compensates the crew when systems malfunction? On Earth, we have legal frameworks for accountability, but these assume timescales of human lifetimes and governments that persist. A generation ship would outlive any legal entity that launched it. the crew would be legally orphaned, with no recourse, no representation, no rights. It's indentured servitude on a cosmic scale. Recent discoveries about stellar metallicity show that stars differ in their elemental composition far more than we thought. Some stars are metal-poor, others metal-rich. This affects the planets that form around them and the radiation environment they create. We're selecting target exoplanets based on observations that tell us almost nothing about the actual conditions there. We'd be launching thousand-year missions to worlds we've never truly seen based on guesswork and wishful thinking. The nitrogen problem illustrates how even simple resources are impossibly complex. Humans need nitrogen for proteins and DNA. Plants need it for growth. It's essential and irreplaceable. On Earth, the nitrogen cycle involves bacteria, plants, animals, soil chemistry, and atmospheric processes in complex feedback loops. Replicating this on a spacecraft would require maintaining bacterial cultures and ecosystems for millennia. If the nitrogen cycle broke and complex systems always eventually fail, the crew would face slow starvation regardless of other resources. Consider the documentary record problem. We think in decades, maybe centuries at most. Institutions try to preserve records, but libraries burn, hard drives corrupt, languages change. The Rosetta Stone required decipherment because ancient Egyptian was forgotten. Over the timescales of interstellar travel, the ship's logs and mission parameters would become unreadable. The crew would forget where they came from, why they're traveling, perhaps even that Earth exists. The mission itself would be lost to time. The gravitational wave observatories like LIGO remind us how sensitive detectors must be. LIGO detects distortions smaller than a proton in equipment kilometers long. This precision requires isolation from every vibration, temperature change, and electromagnetic interference. A generation ship full of people, machines, and biological processes would be impossibly noisy by these standards. Any sensitive scientific equipment would be useless. The ship couldn't do serious science en route. It would just be a tube full of struggling survivors. The evolution of pathogens presents another biological time bomb. Viruses and bacteria evolve far faster than humans. They can go through millions of generations while we experience one. In the closed environment of a spacecraft with stress-weakened immune systems and limited genetic diversity, pathogens would evolve to become more virulent. Historical ship voyages saw disease spread rapidly in confined conditions. A generation ship would be a plague incubator with no possibility of outside medical intervention when new diseases emerged. The discovery of the interstellar object Oumuamua in 2017 showed us that stuff travels between star systems naturally. This first detected interstellar visitor was tumbling oddly, accelerating slightly, and shaped like nothing we'd seen. If we're detecting one interstellar object with our limited observational capabilities, there must be millions out there. Each one is a potential collision hazard for interstellar craft. Space between the stars isn't empty. It's a shooting gallery of debris we can't track or predict. The Kessler syndrome, a cascade of collisions creating exponentially more debris, threatens even Earth orbit. Imagine this on interstellar scales. One impact creates fragments traveling at relativistic speeds. Those fragments hit other objects, creating more fragments. The space between stars might already be full of collision debris from ancient civilizations' failed attempts at interstellar travel. We might be navigating through a cosmic junkyard of civilizations that tried and failed before us. The solar sail experiments we've conducted, like the Planetary Society's LightSail 2, revealed unexpected problems. Solar sails are fragile, easily damaged, difficult to control. They require perfect deployment and constant orientation adjustments. Scaling this to interstellar distances where the solar wind becomes negligible would require sails kilometers across, mechanisms that work perfectly for centuries, and navigation systems beyond our current capabilities. What seems elegant in theory becomes impossible in practice. The deep time problem makes planning absurd. We're terrible at thinking even 100 years ahead. Climate change, resource depletion, biodiversity loss, all problems requiring long-term thinking we're failing at. How could we possibly plan a mission lasting 10,000 years? Our assumptions about future technology, resources, political systems, and even physics could all be wrong. We'd be committing resources and lives to a mission based on guaranteed to be incorrect predictions. The Copernican principle suggests we're not special. We should expect to find ourselves in typical, average conditions. If interstellar travel were possible, we'd expect to see evidence of it. We'd expect alien probes, megastructures, signs of civilization spreading between stars. The Great Silence suggests strongly that interstellar travel is simply impossible for any civilization, no matter how advanced. We're not failing to reach the stars because we're too primitive. We're failing because everyone fails. The universe has set barriers no one can cross. As we near the end of this cosmic reality check, let's confront the most profound barrier of all. The universe's architecture seems deliberately designed to isolate civilizations. The speed of light isn't arbitrary, it's woven into the fabric of causality itself. The vast distances between stars aren't accidental, they're consequences of the universe's expansion history. The fragility of human biology isn't a flaw, it's the natural result of adaptation to Earth's specific conditions. Every barrier we've discussed emerges from fundamental physics, and fundamental physics doesn't negotiate. The sad irony is that the golden age of exoplanet discovery coincides with our growing understanding that these worlds are unreachable. We're finding potentially habitable planets at an accelerating rate. The Transiting Exoplanet Survey satellite has discovered thousands of candidates. Ground-based surveys detect more every month. Future telescopes will characterize their atmospheres, possibly detecting biosignatures. We might confirm that life exists on dozens of worlds. But we'll never touch them, never sample their soils, never meet any inhabitants they might harbor. Consider the perspective this gives us on Earth. Every element heavier than hydrogen was forged in the nuclear furnaces of dying stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all created in stellar explosions billions of years ago. You are literally made of stardust, but that stardust has only one home where it can take the form of conscious, curious beings, this blue marble orbiting an ordinary yellow star. Earth isn't just our home, it's the only possible home in an unreachable universe. The failure to reach other star systems isn't humanity's failure, it's physics succeeding. Einstein's equations work. Thermodynamics is inviolable, biology has limits. These aren't bugs in the universe's code, they're features that make the universe stable, predictable, and ultimately knowable. If faster-than-light travel were possible, causality would break down. If interstellar distances were smaller, stellar interactions would destabilize planetary systems. The barriers keeping us here might be the same barriers that allowed life to evolve in the first place. Recent measurements of the universe's expansion rate, the Hubble constant, reveal an accelerating expansion that will eventually isolate our local group of galaxies from all others. In about 100 billion years, all galaxies beyond our local group will have receded beyond the cosmic horizon, unreachable even at light speed. The observable universe is shrinking. We're living in a brief cosmic moment when other galaxies are visible at all. Our descendants will inhabit a lonelier universe where most of the cosmos has vanished from view. But here's the perspective shift that changes everything. Perhaps the purpose of intelligence isn't to spread across the galaxy. Perhaps it's to understand the galaxy from one vantage point. We can study the entire universe from Earth, detecting gravitational waves from colliding black holes, analyzing light from the universe's first galaxies, mapping the cosmic web of dark matter. We can't touch these phenomena, but we can understand them. Maybe understanding is more profound than presence. The search for extraterrestrial intelligence, SETI, takes on new meaning. We're not looking for neighbors we might visit. We're looking for fellow prisoners, other civilizations trapped in their own stellar systems, separated by unbridgeable gulfs. If we detect an alien signal, it will be from a civilization we'll never meet. We'll be cosmic pen pals, exchanging messages across decades or centuries, forever separated but connected by curiosity and the shared experience of isolation. The resources that might have been spent on impossible interstellar missions can be redirected to preserving and exploring Earth. Our planet is more alien and less explored than most people realize. Deep ocean trenches host creatures as bizarre as anything we might find in space. Extremophile bacteria reveal that life's possibilities are stranger than we imagined. The complexity of Earth's ecosystems exceeds our current understanding. We haven't finished exploring our own world, yet we dream of others. The cosmic perspective reveals that rarity equals value. Earth isn't just one planet among trillions, it's the only one we'll ever stand on. Every forest, every ocean, every mountain range becomes infinitely precious when you understand it's all we'll ever have. The stars aren't destinations we'll reach, they're beacons reminding us how special our home is. Our isolation doesn't diminish us, it emphasizes our responsibility to preserve the only harbor of consciousness we know in an ocean of unknowing. Future generations won't curse us for failing to reach the stars. They'll thank us if we preserve Earth, if we pass on knowledge, if we maintain the wonder that makes us look up at the night sky and ask, why? The dream of interstellar travel has driven technological innovation, inspired countless people to study science, and expanded our understanding of physics and biology. The dream has value even if the destination is unreachable. Perhaps the universe's isolation is its gift to us. Without the possibility of escape, we must confront our problems here. We can't abandon Earth for greener pastures among the stars. There are no greener pastures. Climate change, resource depletion, species extinction, these become existential imperatives when you understand Earth is all we have. Our cosmic cage might be what forces us to finally grow up as a species. The atoms in your body have been on an incredible journey. They've been inside stars, in stellar explosions, in molecular clouds, in the solar nebula that formed our planets, in rocks and oceans and bacteria and dinosaurs. They've traveled through space and time to be here, now, arranged in the pattern that is you. And they'll continue their journey long after you're gone, becoming parts of future stars, planets, perhaps even future beings. You're not separate from the cosmos, you're part of it, experiencing itself. So while we'll never reach Proxima Centauri b or TRAPPIST-1e or any of the thousands of exoplanets we've discovered, we can still explore them with telescopes, understand them with physics, and appreciate them with wonder. We can look at our night sky and know that nearly every star has planets, that the universe is richer and more diverse than we imagined, even if most of it is forever beyond our reach. The universe is vast and we are small. The stars are unreachable and we are mortal. The distances are unbridgeable and our technology is limited. But none of this diminishes the miracle that we exist at all, that the universe has organized itself into beings capable of contemplating its own immensity. We might be trapped on one world, but our minds can wander among the stars. And perhaps that's enough. Thank you for joining me on this sobering but hopefully perspective-giving journey. If this exploration has changed how you see Earth and our place in the cosmos, please share it with someone who needs that cosmic perspective. Subscribe to continue exploring both the limits and the possibilities of our universe. Remember, we might be forever Earthbound, but Earth orbits in space, flies through the galaxy, and participates in the universe's grand story. We're not imprisoned on Earth. We're riding it through the cosmos, the only life-bearing world we know in an incomprehensibly vast universe, and that makes us, and our home, more precious than all the unreachable stars combined. Until next time, keep looking up at those distant, impossible stars, and remember they're looking back at the only world that created beings capable of understanding them. We are the universe, knowing itself. That's not a consolation prize, that's the greatest achievement in cosmic history. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. How big is the solar system and why we will never leave it? In this video, we reveal the true, mind-blowing scale of our solar system, from the blazing sun and the orbits of Mercury, Venus, Earth, and Mars to the gas giants and much more. See you there.